Do you have any questions? Okay, so if not, let me continue in the discussion of the interacting theory. And what I want to do now is to move beyond the three-point function and to give you some example of non-trivial four-point functions from which I think you can see what the pattern is for more general amplitudes, right? So as someone already pointed out, the case of the three-point function looked very special because it saturates perfectly the anomaly of the BC system, right? And you get automatically a result that does not depend on the insertion of your local operator, right? But what happens for a four-point function where we would naively write, right, in an open string setup, right? Something like that. Now this brings me to discussing the other bit of the Faddeev-Popov determinant that we introduced in the covariant description, which has to do with the B ghost instead of the C ghost, right? So if you remember, what we said is that we rewrite the determinant as a path integral over Grassmann variables, and that path integral represents the square root of the determinant of P dagger P, and P dagger is now the operator doing the inverse operation, so mapping the tensor traceless B field into one forms, right, into the C, right? So the question now is, are there zero modes for the B ghost? So this would be a problem similar to the one we addressed for the C ghost, right? Because in the path integral measure, you have both terms, and if one of the modes of the B ghost is a zero mode, so is a solution of this type that is acceptable, then again your four-point correlator would be naively zero unless you have the insertion of that zero mode that makes the Grassmann integral finite, right? So we did not worry about this fact, because by following the very same calculation that we did for the C, but adapted for the B, remember B is a field of weight 2, 0. So think about B as something like this, right? So if you repeat the same calculation that we did when we moved from the North Pole patch to the South Pole patch, you will see that the Yacoubian comes in the opposite direction, because this has weight 2, 0 instead of -1, 0. So this has the Yacoubian in the opposite direction. And so the Yacoubian works against you, right? So you will not find any regular zero modes on the sphere for the B ghost. So that's why we didn't care about that problem, right? We didn't have any zero mode to worry about. But now, think what happens in an amplitude like that, right? An amplitude like that is describing, from the mathematical point of view, a worldsheet that is indeed a sphere, but it has 4 special points. Z1, Z2, Z3, and Z4 are special because in those points we inserted a local operator. So now we'll interpret this equation, right, as an equation of a B field that lives on a sphere except 4 points, right? We have to take away these 4 points, and we have to take away these 4 points because if B is very close to one of those 4 points, there is a singularity due to the OPE between B and C. So from the 4 point on, right, we have to ask whether there is a solution of this equation that is regular everywhere except in 4 points. And in those 4 points, we have to have a pole-like singularity. Right? Because when B, so you are in your C, 4 points, right? And then you have BZ, right? When BZ goes very close to Z1, right? BC goes like 1 over Z over Z1, 1 over Z minus Z1. Now, you can easily find solutions of this equation, right? Just write a meromorphic function, right? And it has the right pole structure, right? You just write 1 over Z minus Zi product I from 1 to 4. Right? So as a function of Z, this one has simple pole around Z1, Z2, Z3, and Z4. Now, you can ask, is this function regular at Z equal infinity? And then you can repeat exactly the same calculation, right? You multiply by dz square, you do the Yacoubian, and now you will see that this object is regular at Z equal infinity. Because the Yacoubian grows, but you have 1 over Z to the 4th coming from this bit. So this is a very simple calculation. Please do it. It's following on the same steps that we did for the C ghost. And it's crucial that you have 4 points, right? If you take 1 point away, you can again find a solution such as this one that has a simple pole around 2, 3, and 4. So this product will go only from 1 to 3. That solution exists, but will be singular at Z equal infinity. The Yacoubian will go as the 4th power. So this simple calculation shows that you start worrying about zero modes of the B field only from the 4-point function on. Is this clear? And it is not difficult to realize that if you have an n-point function at 3 level, you will have n minus 3 zero modes that are completely independent. So I will focus on the 4-point function, but the same calculation you can do it for higher point function. So the question is, what shall we do with this zero mode? It seems that the 4-point function, this integral contains an integration over this corresponding to this zero mode, and there is no B field anywhere. And so we go back to the problem of having a Grassmann integral that kills everything. Now, the idea is the following. Is that you actually can trade, so you can do a change of variable. It's nothing more than that conceptually. You can do a change of variable where you trade the integration over this zero mode for the integration over one of these z's. So this means that if you keep fixed z1, z2, and z4, right, and you just change z3, you get configuration that are not equivalent. So you can do a change of variable that transforms the integration over these zero modes for the integration of one of those z. So I will not go through the precise steps, but I will just mention some words. So if you want to read more about this, you maybe are helped. And if you have questions, of course, please ask me. So the idea is that there will be a Yacoubian, right? Anytime you have a change of variable, you have a Yacoubian. And this Yacoubian is between the zero mod B and the formation of this position of this Z3. That the Yacoubian, from the mathematical point of view, is done by calculating the overlap between this zero mode and an object which is called Beltrami differential, which encodes the infinitesimal deformation of the position of Z3. So you will have a B, Z, Z, mu, Z bar Z integral. Right. So this is this object, is the zero mode. And this I will not define precisely in the lecture, but it's basically an object that has weight +1, -1, right? Left and right. And it encodes the deformation, the motion in the zeta3, which basically tells you a motion in the moduli space of different puncture Riemann surfaces. I will not be very precise about this because you can do the calculation in this three-level case, and this Yacoubian is 1. Right? So that's easy. But you see that basically what this object does, it takes away one factor of C. In this case, I'm choosing, I think, zeta 3. So I keep fixed 1, 2, 4. Let me check whether this is what I do. And then you start moving zeta 3. So basically, this Yacoubian takes away one factor of C, and the correlator you need to calculate is d zeta 3 CV Z1 CV Z2 V Z3 CV Z4. Now, if you look at this expression also from the two-dimensional point of view, it makes sense. This object has conformal weight 0. This object has conformal weight 0. This object instead has one C less. C had conformal weight -1. So when we take away the C, this object will have conformal weight 1. And so it can be integrated. And this is again conformal weight 0. So the message is every time you have a zero mode for the B field, you trade that zero mode for an integration over inequivalent surfaces. And this is the mathematical rephrasement of the physical intuition that I mentioned at the beginning, at some point in the lecture in the morning, saying, oh, the path integral philosophy is that you will have to integrate over all inequivalent surfaces, right? In the case of the three-point function, there are no inequivalent surfaces that are smoothly connected. In the case of the four-point function, well, you have one parameter of inequivalent surfaces, and so you have one integral. If you add more and more external states, you will have more and more zero modes, and you will have more and more integral to carry over. Do you have any question about this?
The integral you wrote with the mu, is that the measure inside the mu, or
is the Yacoubian? Is the Yacoubian. So it's the thing that moves you from the integral over the B field to the integral over the Z3.
Okay.
It doesn't appear? Here. No, because we already did it and it's 1. That Yacoubian is just 1. It's just because it's easy. When you start doing loop amplitude, that Yacoubian will be more complicated. You have to calculate it explicitly. More questions? Okay, very good. So now I have all the technology to give you the result of the first 4-point string amplitude, which, let me stress, funnily enough, is the very first formula that was written in, if you want, in string theory in 1968 by Gabriele Veneziano. So without doing all this, it was just basically invented from the thin air because of all its nice property. And then people went backward to provide a background for this formula. So that formula describes the case where this V is e to the ikx. And for the open string case, as before, right, this x left and x right identified, they cancel in the Dirichlet direction, and so it will become e to the 2i k x left. So the calculation for the point of view of the conformal field theory is very similar to the one that we did for the 3-point function, but now you have 4 terms, right? You have to contract this one with this one, then the result with this one, and then the result with this one. So I will write the final result and just tell you where each term comes from, and then you can, if you want, fill the details. So the final result will be this. And then let me use the convention Zij, Zi minus Zj. Right? So the final result will be Z12, Z14, Z24. This is from the Gauss sector. So this is exactly what we did before. Nothing has changed. We only have 3 C's. And so this is from this one, and this one. You extract the terms proportional to C minus 1, C0, C1. Pay attention to the signs. You will get the same thing as before. Then you have the bit that comes from the ikx in all the 4 bits. And then with a bit of work, what you get is Z12, Z34 divided Z13, Z24, Z14, Z23 divided Z13, Z24. And then, in order to write the exponent, let me introduce the Mandelstam variables. So this is the S variable. So this is exactly what one does in quantum field theory. I don't know whether my conventions are kosher, but let me write them so that at least the notes are self-consistent, right? And then you have alpha prime K1 plus K4. So these are the Mandelstam variables, so the same thing that you would write for a scattering of 4 scalars or 4 particles anyway. And now this exponent, exactly as before, will be K1, K2, K1, K3, right? All these dot products. And you can rewrite those dot products by using momentum conservation and non-shell condition. You can rewrite them in this term, in terms of these Mandelstam variables. And the result of this calculation is that these exponents are minus alpha s minus 2 minus alpha prime s minus 1 minus alpha prime t minus 2 minus alpha prime t minus 1. Here we are using also that ki square is 1 over alpha prime. So you use momentum conservation and on-shell condition. So this comes from the matter sector. Very good. So this looks definitely like a function that has a non-trivial dependence on the z, right? So we don't expect the miracle as before, that all the z disappears. This is a non-trivial function that we need to integrate. But still, it's not in the form we like, because we would expect that this integrand depends only on one variable, not on these ones. Should not depend on the variables that should depend only on one combination of these Z1, Z2, and Z3 and Z4 variables. We should have only one integral. We only have one zero mod for the B field. So in order to make this manifest, it is convenient to introduce the following variable. You will see more and more of this in your CFT lecture. This part is common not just to the CFT in two dimension, but to the CFT in general. The nice property of this cross ratio, right? So this is Z1 minus Z2 times Z3 minus Z4 divided Z1 minus Z3, Z2 minus Z4, is that this cross ratio is invariant under the SL2 transformation that are the residual gauge invariants related to the C. So this is an algebraic calculation that you should do. Let me just finish this, and then that you should do once just to check, right? So if you take each Zi and send it in I Zi plus B divided C Zi plus D, so you do it in the numerator and the denominator, you do common denominator, you use the fact that this AD minus BC is 1, the determinant is 1, you will see that this combination does not change, is invariant. Yes, thank you. Thanks very much. Yes, sorry. More questions? Right. So, this observation is, if you wish, a more concrete version of the fact that there is one zero mod in the B, that there are inequivalent surfaces, right? You can take values 1, 2, 3, 4. If this cross ratio takes different values, then you cannot link the two things by using the residual gauge transformation. So the natural thing, the natural way of writing this correlator is to write it in terms of this variable, not of Z3, but of that cross ratio. And so we do yet another Yacoubian, right? So you can calculate this Yacoubian, dz over dz3, and then you invert it. This Yacoubian will take this form. So you just calculate it from here, right? It's trivial calculation. And you will get this form, Z13 square, Z24 divided Z12, Z14. So this is Yacoubian. Now, if we look at what happens, right? So we should have that the all integrand becomes a function of this Z. So let's see. 1, 2 cancels 1, 2. 1, 4 cancels 1, 4. And then we have 1, 3 square, 2, 4 square, right? Which I can combine with the numerator, changing this to minus 2. And this to minus 2. I take one factor of 1, 3, 2, 4, I put it here, and I take the other factor of 1, 3, 2, 4, I put it here, and take away that. So the final result is that my integral for the 4 tachyon amplitude is an integral over this cross ratio. And then 1, 2, 3, 4, 1, 3, 2, 4 is exactly Z. So I have Z to the minus alpha prime S minus 2. And now you can see that this slightly different cross ratio, 1, 4, 2, 3, The denominator is the same as before, but the numerator is slightly different. It's a different permutation of the indices 1, 2, 3, 4. The key point is that all 4 indices appear once, both at the numerator and the denominator. Any of such combination can be written in terms of z, and it's a very easy exercise to see that that combination is just 1 minus z. Do the common denominator, expand, 4 terms, cancel. And so you have this. And so, as I advertised, you see, this is a bit a cross-check that all the steps are correct. When written in the right variables, this amplitude depends only explicitly on one combination, which is this SL2 invariant cross ratio. And that dependence has to be integrated over. Now, what is the range of integration? Well, keep in mind what the picture is, right? The worldsheet is the upper half plane, right? Sigma equals 0 is this boundary, this is the other boundary. And if you are considering one color order calculation, then you have a fixed ordering, right? So we are considering 1, 2, 3, and 4. Now, originally we had an integral over zeta 3, and we see that zeta 3 can go from zeta 2 to zeta 4. That's the range of integration of zeta 3. Then we change variable from zeta 3 to z, and so we can see what is the range of integration over z, right? So when zeta 3 is equal to zeta 4, that factor vanishes, so z is 0. So the lower integral here is 0. Now the opposite limit is when zeta 3 is equal to zeta 2. And then you see that when zeta 3 is equal to zeta 2, this cancel this, and this cancel this, so zeta goes to 1. So this color order contribution is described by this integral. And this integral was not the end point of this derivation, but was the starting point of the paper by Veneziano, because this integral can be written in terms of gamma function. So this is gamma minus alpha prime s minus 1, gamma minus alpha prime t minus 1, divided gamma of minus alpha prime s minus alpha prime t minus 2. And this guy is nothing else than the Euler beta of minus alpha prime s minus 1 minus alpha prime t minus 1. Right? If you want, this is a definition. Any question on this derivation? Now, if you want to, this is one ordering, right? And you see this puncture tree can go from 2 to 4. It cannot go beyond because it would need to get out of the boundary and come in. This is not allowed, right? So the contribution when 3 goes on this side, when 3 is on this segment, and when 3 is on this segment, there are 3 independent contributions. Exactly as we did for the 3-point function, we have to sum over them, right? These are the non-cyclical permutation of the external legs 1, 2, 3, 4. So the full tachyon amplitude, and that's formula very similar to one that was written in the paper by Veneziano. I write it in a modern language, so I put already d equal 26. Of course, that was not in the original paper. Momentum conservation. And then I have 3 Euler beta. This is the one we calculated, and then the other results are very easy. You just take that and do the permutation between 1, 2, and 3, and keep for the fixed. Right? Those are the non-cyclical permutation. You will have 3 independent structures that are these. Now, you see, as advertised, what we have, it's an amplitude that depends on the Mandelstam variable, and we have taken care of all the worldsheet properties. Any questions? Yeah. Yeah. This picture here. Oh, yeah. Very good, sorry. So here the argument was done in general. So I was thinking about the sphere. So you will have a 0 mod for the B and a 0 mod for the B tilde, right? So you can deform Z both along the real axis and the x-axis and the y-axis. When you move to the open string case, as usual, you don't have the two as independent. They are identified. And you have only one 0 mod. The two are identified, only one 0 mod. And that 0 mod describes the deformation just along the real axis. Keep in mind, the open string vertex operator are not allowed to go inside. They're only allowed to move on the line. That's why this is a real integral. I will come back, I hope by today, to the closed string case. And as you can guess, the closed string case will have a complex integral, d to z. And there is a fun story, which, okay, is a bit maybe advanced, but I want to give you a flavor. Someone of you mentioned the KLT story. That's interesting. I'll try to give a summary of that. More questions?
In the closed string case, how do you pick the limit of integration equals 3? Because in the open string, we're locked onto the axis, and it's very simple.
Yeah, you will see. Yeah. Let me. But I mean, the short thing is that you will integrate over all the complex plane. Right? There is no cyclic ordering for the closed string. So the integral is over everything. And okay, let me just give the punchline here. So from the worldsheet derivation, there is a clear suggestion that there is a relation between the amplitude for the closed string and the amplitude for the open string. One bit of the relation is obvious to you already now. And the bit that is obvious is that the integrand will be calculated by doing the conformal field theory correlator separately on the left and on the right. So the integrand, the bit which will be inside, will be a product of a function of z and a product of a function of z bar. But what is non-trivial is that also the result of the integrand, the integral, will also have a factorized property. And that means that the amplitude of gravity can be seen as the square of the amplitude of the open string, so of gauge theory. So this is something that from the field theory point of view is completely unexpected, but from the worldsheet point of view, you will see it is natural. So from this KLT relation, there has been a kind of inspiration and many developments that took that, and you can say, okay, let me study this now independently and see how far I can go. More questions? Okay, so what I want to do now is to pause for a moment the analysis of the worldsheet before going into this, and describe a bit the space-time properties of this amplitude. And the message I want to convey is that some of the properties are similar to what you expect in field theory, and some of the properties are very different. right? So what I want to highlight is what are the stringy feature, the new things that you'll see in this amplitude. And this stringy feature were those that kind of attracted the attention of Veneziano in '68. So let me give you now a cartoon of this process in space-time. And I focus in particular, so this is very much as in QFT, right? You have a 4-point amplitude, and you can write this 4-point amplitude in the forward limit, which means I take 2 of the external particle as ingoing particle and 2 of the outgoing particle, and I'm thinking about this as a scattering process, right? So in space-time, I literally have particle 1 and particle 2. I can always choose a center of mass frame, where one particle comes from the right, one particle comes from the left. These particles are identical, so they're the same momenta, but opposite direction, right? And then I have particle 3 and particle 4. And so this is 3 and 4. And this angle theta, right, is deflection angle, right? So is particle 2 coming in and being deflected and becoming particle 3. Now, you can make a very explicit choice of momenta, right? So you can choose, for instance, let me just give a flavor, K1 as the center of mass energy divided by 2, and then some K, this is the space-like part. Then if there are Dirichlet direction, this will be 0 in the Dirichlet direction. Let me not write that, right? The open string moves only along the brane. Then K2, the second incoming string will bring the other half of the energy. And then the momentum will be the opposite, right? So this is the ingoing momentum. And then you have K3 and K4. And K3 being an outgoing particle, it has negative energy, right, as we do in quantum field theory. And then it will have a K out. K4 will have minus K out. Right. Now, this vector-like momentum, if you do K in dot K out, the spatial component is proportional to the cosine of this angle, right, cos theta. So you can rewrite the Mandelstam variable, and let me rewrite minus T over S in terms of the center of mass energy and the angle. And it's an easy exercise, just by using that kinematics, right? And on-shell relation, right? That this minus T over S is sine square theta over 2. Okay. It's nothing mysterious. This is the same. There is no string theory. This is just kinematics, and it would be the same kinematics you would do for a field theory amplitude or for particle of the same mass. And what I want to just stress is what is the relation between this Mandelstam variable and the physical variable of this scattering process. Now, what you expect is that this string theory amplitude will be similar to field theory amplitude if the energy of the process, the typical energies involved in the process, which are captured by the Mandelstam variables, right? K1, K2 is S, K2, K3 is T, right? So the Mandelstam variable S, T, and U will contain the typical energy scale of the process. If those typical energy scale of the process are much lower than the string scale, then you would expect that this looks like very much field theory. So we have seen a similar thing when we were discussing the 3-point function of the vectors, right? There was a bit which was the field theory, and then some plus 2 alpha prime, something that was with 3 momenta instead of just 1. So here in very much, right, you can think if S is much lower than the string scale, then alpha prime dot s is small. I will be able to expand this thing for small values of alpha prime s, alpha prime t, right? And I should recover some form of field theory. So this is a low energy limit that I will discuss, but not for this amplitude. I will discuss for a supersymmetric cousin of this amplitude because it's nicer. In that case, you will make contact with massless degrees of freedom, right? The problem is that this object, the mass of this object is stringy. The mass of the tachyon is over 1 over alpha prime. So let me postpone the analysis of the low energy limit, but keep in mind this picture that if the Mandelstam variables are small with respect to the string scale, we expect to go over a regime where the string theory is very similar to a field theory. And then you can ask yourself, what is the regime where the string amplitude is actually very different from a field theory amplitude? And of course, it's the opposite regime, right? So of course, it's the regime where you have a very energetic interaction, and at least some of the Mandelstam variables are much bigger than the string scale. So we are doing a limit where alpha prime s is very big. So this is an high energy regime, which is interesting because it shows the stringiness nature of the amplitude. And you have two regimes that I will briefly discuss, and then you see often written in the literature. One regime which is called Regi limit. And this regime is a regime where alpha prime s is big, but t over s is small. So notice that s is k1 plus k2. So when you take there k1 plus k2, the momentum disappears. So only the zero component. So S is nothing else than the energy of the center of mass square. So taking alpha prime S to be very big, it means that you are scattering the two particles at a very high energy in the center of mass. But taking T over S to be small tells us that the deflection angle is very small, right? Because the deflection angle is T over S. So this Regi regime describes a process where you have the two particles scattering with a large center of mass energy, but at a very big impact parameter. They are far away from each other. So the interaction only deflects the particles a bit. So this Regi limit is, from time to time, called also small angle, right? Because theta is small. The other regime is the fixed angle. Right? Fixed angle means we are taking alpha prime s to be big and alpha prime t to be big, such that T over S is fixed. The angle is fixed. So in this picture, we are trying to lower this impact parameter in such a way that the two objects that moves very energetically against each other really crash against them, right? The impact parameter is small. Any question on this space-time picture? Okay, so let me start from the second one. And, but okay, let me first say a general comment. As you can guess, you see this result is written in terms of an Euler beta, and the Euler beta is nothing else than the gamma function. And now we are taking these parameters to be very big. So the key mathematical result that you just need to apply many times to find, to extract the physics here, is just the Stirling approximation, right? The gamma function is the generalization of the, and then this is like taking n factorial, where n is very big, right? Because these things start being big. So let me just write for you what the Stirling approximation is, and then I will not do all the steps, right? They take like 5 minutes each. You just have to be careful, do it on each gamma function. But the key result we'll use is gamma x is an asymptotic formula that holds for very large x, and this is even more precise than what we need in most of the calculations. So basically what I'm saying is that if you take alpha prime s and alpha prime t to be big, then this is big, this is big, this is big, right? And so you have to take each of these gamma, plug, use that expression, and you write it as exponential of something, and then you just have to simplify that exponential. So it's nothing strange, right? This is just a straightforward calculation. It's a bit boring, right? And it helps doing it for number 2. For number 2, it helps tackling this limit after a massage on the amplitude. So let me write this amplitude in another equivalent form, and if you want, you can check that is equivalent. I'll tell you how you do it. So the equation that you have above, right? Let me focus on the square parenthesis. Can be written in equivalent form as gamma minus alpha prime s, gamma minus alpha prime t, gamma minus alpha prime u, and then sine sine. Right, so this is a more symmetric formula. These 3 terms combining these 3 terms. How do you get there? Well, the relation you need to use is another property of the gamma functions. Right, so you need to use momentum conservation. So this guy st is related to u. You have s plus t plus u. Momentum conservation tells you that is 4 over alpha prime. So you need to use momentum conservation, and then in a wise way that relation, and that's why you get these signs. Now, once you have written this in this form, you see you have a fewer number of gammas. That was the goal, right? Then you have to apply this relation every time you see a gamma, and now you have only 3, right? And there you had 3 per each term, so you had 9 gammas. So what you can do is apply the Stirling formula on this relation, and this combination here should take the form, right? This gamma will be the exponential of something, right? So apart from numerical factors, right, the leading behavior, the exponential, will take the form of minus alpha prime s log alpha prime s plus t log minus alpha prime t plus u log minus alpha prime u, right? No surprise, this comes from this gamma function, this comes from this gamma function, this comes from this gamma function. And once you have done that, you can start using these kinematics, right? And S is just the energy of the center of mass square. T is minus S times sine square theta. Right. And what about U? Well, it's a little algebra that in the large energy limit, right, in this limit number 2 that we are considering, U will be minus S cos square theta. So what you can do is to rewrite each of these factors in terms of the energy and the angle. And the result takes this form. So this term will combine with this term, and they will combine just in these two combinations, one that has the log of sine square, and the one that has the log of cos square. So this is just mathematical steps, right? You take your amplitude, you go to very high energy in the regime when the angle is fixed. You apply Stirling identity, Stirling approximation, and then you can rewrite the gamma function, and this is the leading behavior of the gamma function. So what I just want to convey is that there is nothing mysterious, right? It's just an algebraic calculation. But the result is very interesting, because the sine is a function that is only between minus 1, 1. So sine square is a number between 0 and 1. And cos square, the same, is a number between 0 and 1. So this combination here is always negative, right? Is the log of a number that is more than 1. And the same for this combination, it's always negative. So the whole square parenthesis is always negative. And you see, this is the exponential of alpha prime center of mass energy square, right? This is this factor S that we took as an overall factor, right? And then in this regime, this is a very large number. So this is showing that this amplitude is very, very small. It's exponentially small when you calculate it at very high energy and fixed angle. That's completely different of what happens in a quantum field theory, right? When you lower the impact parameter, right? You have large scattering, like the Rutherford experiment, right? So this is really a signal that the objects that are scattering are not point-like. They are not point-like, that you can make them closer and closer, and the closer they are, the bigger the force they feel, and so you have large scattering. These are extended objects, and if you make the impact parameter too small, instead of having an hard interaction between 2 points, you have a crash of 2 extended objects, right? And different bits of the string will pull up and down. And so it's very unlikely that they will all contribute in the same direction and have a large deflection. So this is one of the properties, if you want, that kills the naive idea of applying all this directly to hadronic physics, right? Okay, any question about that? So this stringy feature, right? Very suppressed interaction at fixed angle. Now, the answer, okay, just a comment. This is a bit of a tricky answer, right? Because if I calculate some three-level amplitude, and this three-level amplitude is super small, then you may wonder that maybe your perturbation theory is not very sound, right? Because the perturbation theory assumes that the three-level amplitude is bigger than the one-loop amplitude, right? So if this is already super small by itself, I mean, are we sure that the corrections are small? So it's actually hard to solve this problem exactly. But this is kind of the message that's coming out. If you just forget all the loop correction, just focus on the first calculation you can do, it conveys the idea that the interactions are very soft. Very good. Any question on this? Okay, so let me, before the break, make some comments on the other regime. And technically, the calculation is not that different. It's again applying Stirling formula. But now the application of Stirling formula is a bit asymmetric, because you see, we are treating S and T in a different way. Right. So it is convenient to have an intermediate result. So let me give you what the intermediate result is, and then you can check, and then if you want, you can apply it. But it's just a consequence of Stirling formula. If you have a ratio of gamma functions, and this A becomes very big, notice that this is exactly of this type, right? So we have alpha prime S, so that's this A becoming very big. And then I have two independent shifts, B and C. Here B is -1 and C is minus alpha prime T minus 2. So this is the type of combination on which we have to apply the Stirling formula. And this has a very easy result, is a consequence of that, but is an intermediate result that is useful. And it takes that form. Right. So you can apply this directly on the original formula. There, you have three terms. And if I focus on the first one, then I have that this goes like gamma -1 alpha prime T minus 1, right? This term is untouched, stays there. And then we have minus alpha prime S, right? This is A. And then I have B minus C, which is 1 plus alpha prime T. Right. Sorry? No. So C is this one? This is C. This is B. This is A.
So alpha prime S goes to infinity.
No, alpha prime S goes to infinity. So think about that. Is alpha prime is your string scale. It's fixed, is what it is. And then you are increasing the energy of the center of mass. So this is a trans-string interaction, right? So alpha prime is a parameter characterizing our theory. It's telling us how long the strings are, how stiff they are. That's your part. That's a dimension for parameter entering the definition of what the theory is. And S is something I can change in my thought experiment, right? I can have not too energetic strings, or then if I have imaginary free accelerator. I just increase the energy, and then alpha prime s becomes very big. So I'm applying this formula there, where this number, alpha prime s is a number, s as k square, alpha prime is 1 over momentum square, is length square. So this number is very big, this is 1, this is finite. Now, this behavior, so the fact that the amplitude in this regime, in this small angle regime, goes with this behavior here, is called Regi behavior. Right? And you see, the Regi thing is this function there. That function there is a linear function. And if you remember, this linear function, so if you write this in terms of a graph, is exactly the graph of the leading Regi trajectory. The one that starts with the tachyon, then has a second state, the vector, and has more and more energetic states that have a fixed ratio between the J, the angular momentum, and the energy square. Right? So this suggests, and you can check, I will not do it, but it's possible to do it explicitly, that in this limit, what is actually happening is that in the exchange, so the states that are exchanged between these two external particles are the states of the leading Regi trajectory. And this number here is the spin of the massless states. So that's why it's 1 in the open string theory, because in the open string theory, the massless state is a vector, so I spin 1. And this correction, which is a negative correction, so if you go back, you see minus t over s is sine square, so t is negative. This correction here is due to the other states in the leading Regi trajectory. Now, this behavior is very different from field theory. Let me just say this, and then we can take a break. So if you think to have a field theory where you couple your external states, your scalar states, to just one single massive state, so you can think, okay, of this leading Regi trajectory, I have the vector, right? So of this leading Regi trajectory, like here, this is the vector. Then I have states with, so this is mass square, this is spin, right? So this is mass square equals 0, spin 1. Then I will have mass square equal 1 over alpha prime and spin 2, mass square over 2 over alpha prime, spin 3, right? And what I'm saying is that this result that we derived from the full string amplitude encodes the information of the exchange in this channel of all these states. Is summarizing all the effect of all these states in the Regi limit. Now, in field theory, you would say, okay, it's strange to have a theory with infinite number of states, right? So what happens if I take only one of such states? I take just this one of spin 2. Spin 1, 2, 3. Right. So what happens if you take that only one state and you say, okay, I couple my scalar particle to a state of spin 3, which is massive. And if you do the calculation, it's a straightforward calculation in Feynman diagrams, you do the minimal coupling, the simplest possible thing you can do, you will see that the power of the energy is equal to the spin. So you will see that this energy, this S, will be at a much higher power than 1. So this is a problematic feature, right? Because it's telling you that your amplitude will grow and grow and grow as your energy increases. So it's very hard to find a meaningful theory, field theory, that contains just one or two or a finite number of massive higher spin states. But string theory provides this for you. If you put an infinite number, a whole tower of massive string states, this will be the result. This will be their effect on the Regi limit. So I just want to stress that this is a stringy feature, right? That you have this tower of states and not just a finite number. Okay, any questions? Okay, so let's have 5 minutes break. Okay, so far we have been discussing the bosonic string, and you may worry that superstring will take even more time just to set up the basics, right? And actually, that may be well true if we wanted to repeat the same first principle derivation. And so let me just say in words what that would be like. Right? So in the bosonic theory, we started from a general not gauged fixed action that contained the embedding coordinates that tell me where the string is in space-time, and the metric. Right. And then we discussed as local invariance that of the diffeomorphism and of the Weyl invariance. In the superstring, what we would like to do is to have a supersymmetric version of this object, where for supersymmetric version of this object, I mean a supersymmetric version in 2D supersymmetry. So this matter field will be promoted to a chiral field, something that has a scalar and a fermion. Fermion, worksheet fermion. Everything is from the two-dimensional point of view. Forget for the time being space-time. And H, your metric, will also need to have a partner, right? The metric is like the graviton, two-dimensional fluctuation of the metric. There will be a two-dimensional gravitino, something that is a spinor with a vector index. Then, instead of only talking about diffeomorphism invariance, I would talk about supergravity in 2 dimensions, right? Local supersymmetry in 2 dimensions. And then I would need to gauge fix that, right? And then there will be partner of the ghost system, right? And so on and so forth. Right? This construction is subtle, and I will not do it. I mean, conceptually, it's clear what we need to do, but it will require a lot of energy. So what I will do, I take a shortcut, which allows you, in a direct way, to take what we have been discussing for the bosonic string and write the correct formula for the superstring. The shortcut consists in the following approach. You take the gauge fixed result, right? So the one that you obtains after gauge fixing. And so here you have X, M, B, and C. And then you supersymmetrize this result, where the super SUSY version is 2D SUSY. Now, you have been studying, I think, 4-dimensional SUSY, so this will be much easier. 2D SUSY is the easiest thing you can do from SUSY, right? Then, as soon as you go beyond that, you will start having indices, alpha, alpha dot. It's complicated, right? So, what is this 2D SUSY? Well, geometrically is also very interesting, because what we can do is to do the SUSY discussion in superspace, right? Did you cover superspace in 4 dimension, right? So now we do a baby version of that, 2D superspace. So if this theory was a theory living on Riemann surfaces, and the only 2 examples that we discussed are the Riemann sphere for the closed string and the upper half plane, which is the disk. But what I'm saying is that these are just the simplest example of Riemann surfaces, right? In the supersymmetric version, this will be a theory of SUSY Riemann, or supersymmetric Riemann surfaces. What is a Riemann surface? Well, a Riemann surface is complex manifold, right? So something that is parameterized by Z. Now, if you take C2 and you impose a complex constraint, you'll get a Riemann surface. What is a SUSY Riemann surface? Well, it's a supersymmetric version of that. You will have one Z and one anti-commuting parameter zeta. Right? So in 4 dimension, you add x and theta. So these are the coordinates, the super coordinates. And then what we do, we take all these fields and we promote them to superfields. So instead of just having an x function of z, we will have an x function of this super coordinate. So from time to time, I'll write the super coordinate like this. So we'll have an x function of zeta and zeta bar, a b function of zeta, and then there will be a b bar function of zeta bar, and a c function of z. Right, so take the fields and promote them as superfields. Now there is a subtlety that while you take a Riemann surface, like a bosonic Riemann surface, as I said, right? Take C2 and impose a constraint, you get a Riemann surface. This is not automatically true for this 1/1 supermanifold. Right, so if you have a supermanifold that has one bosonic coordinate and one fermionic coordinate, is not automatically a Riemann surface. There is an extra condition, and this extra condition is that there exists an object. You can rephrase this in more mathematical language, but let me make it simple, that there is a fermionic object whose square is non-zero in all points in the Riemann surface. So that fermionic object is the supercovariant derivative. So this D is something such that this square is different from 0 everywhere. And you can always find coordinates where this D takes this form. Now, you can easily calculate that, right? If you act D on D, right, the derivative of the Grassmann parameter square is 0, right? Because you never have zeta square, the Greek zeta square, right? You cannot have two Grassmann parameters. So this times this is 0. This times this is also 0, because you have Greek zeta times Greek zeta. So the only non-trivial term is this times this, right? And then the commutator will vanish. The anti-commutator will vanish. So the non-trivial term is this acting on that, and so you will see that d square is d over dc. So you see, that's non-vanish. So is the idea clear? So the shortcut we are taking. Take the bosonic theory. Now think about the worldsheet as a supermanifold. Easy supermanifold because it has one bosonic and one fermionic coordinate. And then think about all the fields that we have. X, B, and C. Each one is promoted to a superfield. So this is the game I will be playing, and I will be with this, I can very easily write for you what the content of the superstring theory is. Any question? Good. So let me take this field, the superfield X, and just do the boring expansion, and the coefficients are just normalization, just convention. So when I take the bosonic case, the Greek zeta to 0, right? I get the first component of this field. I go back and find the string coordinates. So this is like taking, remember, this big Z is Z zeta, this is Z bar, zeta bar, right? You set Greek zeta and Greek zeta bar to 0, and you get back the old bosonic field. And then you can continue expanding this field. So you will have a contribution which is proportional to zeta, right? And the object, so by convention, I put an I here. And the object that I have here is a new field which is encoded in this superfield. And this new field has to be fermionic, right? Because this guy is bosonic, this guy is fermionic. So that's a new field. And then I have this, the bit proportional to zeta bar. And then if you wish, you can have an auxiliary term. So this is telling you that for each bosonic coordinate, you will get a fermionic partner, a 2D fermionic partner that has the same vector index in space-time. You have a psi 0, psi 1, psi 2. So you can think about this object as the partner of the holomorphic part of X, and this object as the partner of the anti-holomorphic part of X, right? X splits in X left plus X right. So X left is paired with psi, X right is paired with psi tilde. Now, what you can do, you can write a super action. So you take the action you know, and you just supersymmetrize it. Right? So to get some supersymmetric action, you know that you have to take the top form of some superfield. So you have to integrate over all possible Grassmann variables, right? So a kinetic term would be like that. And then a natural supersymmetrization of the H-fixed action that we know is this one. So you see, I'm really doing very little work. I'm taking the known result and write everything in capital letters, saying, okay, they are superfilled. And then you can expand, right? So you have x, you plug this here, then you have the derivative, right? The derivative has two terms, the zeta and zeta d zeta, right? So you have to do a little bit of algebra, and then you have to select the top form. The result of this calculation will be, so basically I'm performing this integral, the integral over the Grassmann variable, that's the easy bit. And then, as you know, this brings you from the super field formulation to the formulation components, right? Written in terms just of bosonic variables. And you see, this is much easier than higher dimensional case. So if you let me put here 4 pi then I will get 1 over 4 pi 1 over alpha prime dx d bar x, and then I should get plus psi d bar psi plus psi tilde d psi tilde. And then here you get something that contains only f. Don't remember here, maybe square. This I have to check. So what happens is that the equation of motion of f will be completely decoupled from everything else, so you can set the auxiliary field to 0. Right? So we can forget about this. Yeah. Yeah, thank you. Thanks. So this is telling us that the matter content of superstring theory is the old action that we have, plus an action for the fermionic, the two-dimensional fermionic patterns of the X. So you can think about these extra degrees of freedom a bit as you think about the spin. Right? So these are new degrees of freedom in defining your string. These degrees of freedom describe the geometric embedding of the string in space-time, how it physically vibrates. Right? Exactly as you take an electron, and the position of the electron, the word line of the electron, tells you what the electron is. But knowing the wave, the center of mass wave function of the electron is not knowing the state of the electron entirely, right? You have to tell me whether it's spin up or spin down. That's a new degrees of freedom. So these psi are new degrees of freedom of the superstring. If you want to determine the superstring entirely, you have to tell me where the superstring is and also what these psi's do. Very good. And then what I have to do, I have to give you similar expression for big B and big C. That's easily done. So big B will start. So big B is a fermionic field. So a half integer, a spin with half integer weight. So is beta plus zeta B. And big C is C plus zeta gamma. So as the nomenclature suggests, these, and you see they appear in this, they are repackaged in the same superfield. The beta is the superpartner of B, and gamma is the superpartner of C. So we enriched our spectrum, right? X psi, B, small b beta, small c gamma. Now, let us see what the conformal weight of these fields, right, are. So once you integrate away the Grassmann variable, right, we are back in a formulation in components. This looks like a new conformal field theory, right, which has new fields. So all the technology you know will apply, right? These fields will have a conformal weight, they will have a PE, they will have stress tensor, right? And then we will very easily write down these things by using this supersymmetry, generating them by using supersymmetry, right? So if dz has conformal weight 1, right? And we want these two things to have the same conformal weight, and zeta, the fermionic partner, is more or less the square root of z. So what we want to do is to see that this standard conformal weight 1, and this is the square root of the small z. So has conformal weight minus 1/2. Right. So this combination here has total conformal weight 1/2, which is the same as this one, right? Because this is the derivative with respect to that. So is the opposite of this. So this has conformal weight 1/2. This is conformal weight 1. This is conformal weight 1/2. Right, with this assignment, this is very natural, right? This is just the standard thing you do. And you can see the conformal weight of everything else, right? This guy will be 1/2. This guy will be 1/2. This without any derivative. It's a bit of a strange beast, but no conformal weight, right? This one is conformal weight 2. This one minus 1/2. So this is 3/2. Right? This is conformal weight minus 1. This is again minus 1/2. So this guy also minus 1/2. So once you have the formulation in superfields, it's very easy to derive what the conformal field theory properties of these new objects are. Now, you may ask, what is the interpretation of this partner of the ghost? Well, I briefly mentioned there that if you did the full derivation in terms of an ungauge fixed action which had local supersymmetry, okay, then you had to gauge fix the local supersymmetry, not just the diffeomorphism. That will bring ghosts. This will be this ghost. Right? But with this shortcut we just get, and then we would use that to find what the conformal weight is and what the action is, what the stress tensor is, as we did for the bosonic theory. But here we just derive these quantities by supersymmetrizing the bosonic case, the gauge fixed bosonic case. Very good. Any questions? So what I want to do now is, yeah. Yeah, so this, okay, is the same thing that happens in the bosonic case, right? X, think about X as splitting in the left and the right. So actually, to be honest, this X is not a conformal field. The conformal fields are dx and d bar x, right? So dx pairs with psi, d bar x, which is the right moving part of x, pairs with psi tilde. And then here, so sometimes I forget to say, but you also have the b tilde, right? And these are function of z. B tilde will be function of z bar, and they will have z bar, b tilde, z bar, right? In a closed, and the c the same. In a closed string setup, they will be independent, so you will have a full supersymmetric left sector, a full supersymmetric right sector, and then you can do the open string case, which is just the holomorphic part with the right boundary conditions, and that's what we'll be writing on the blackboard. Let me take just a second to add an extra comment. So, since the left and the right part are completely independent, at a certain point in the mid-80s, a group of people had a nice idea to say, what if I take for the left part a supersymmetric theory and for a right part a non-supersymmetric theory? It's not something that it's immediately obvious that is interesting, right? And it's doable, I mean, but you can do that. You can have a left sector that lives in 10 dimensions, a right sector that lives in 26 dimensions. It's very strange. So this type of theory is called heterotic, because left and right play different roles. But you can construct them exactly with those ingredients. I will not discuss those theories. I will discuss more the type 2 theories where you have the D branes, you make connection with the ADS-CFT. But what I'm saying is that the ingredient that I use, you can use that for that as well. And in that case, the right moving sector would not be of this type. It just will have just the B tilde, not the supersymmetric case. More questions? Very good. So the thing I want to do now is to write for you what the equations are for the stress tensor, and then use the previous results to derive what the OPE of two stress tensor is. And then from there, I will check what is the condition on the conformal anomaly, right? On the central charge, the quartic term in the OPE has to be 0. So I'm doing the same as I did for the bosonic theory, no new concepts, but the difference is that now the stress tensor contribution, the stress tensor calculation, will have many more bits, because each one of these new fields, the beta, the gamma, the psi's, will add new terms to the stress tensor, as it did here. It added new terms to the action. So you see that the general flavor is that the superstring calculation is not conceptually more challenging. It's just technically requiring more patience. So what is the stress tensor? Well, the stress tensor for the X, this guy here, it's very easy to guess. It's just dx dx. Now, this stress tensor will have two contributions, right? A contribution that is without any g, and a contribution, sorry, any zeta, and a contribution that is, sorry, square. Yeah. So, okay. This is the starting point I will have, right? And when I expand this in superfields, right? So I expand this in this zeta, I will have a terms with no zeta and a terms which is proportional to zeta. Now, if you look at this starting point that I brought for you, the starting point is fermionic, because this square is just the standard derivative. So this is bosonic, this is bosonic, this is bosonic, but this is fermionic. So the old stress tensor will be here, will be multiplied by z. So this bit will just be -1 over alpha prime dx mu plus 1/2 psi m psi m. So please do this exercise, right? Take this function and calculate the d of this. The d square of this is very easy, right? It's just the derivative, normal derivative. Then you multiply through the terms proportional to zeta. You see, is the old stress tensor plus a new contribution. And this new contribution is the contribution to the stress tensor due to the new sector, the partners of X. Then there is a fermionic bit here that is independent of zeta, which takes this form. So people call this bit T, stress tensor. And this bit I don't know, maybe G, Polchinski, supercurrent. So this is the generator of the diffeomorphism, and this is the generator of the supersymmetry variation. So you see, the idea is to write supersymmetric expressions. Supersymmetric expressions are expressions that are written in terms of superfield and superderivative. Right? Anything that I write in terms of superfield and superderivative, okay, is a supersymmetric object. And I want to write the supersymmetric expression in such a way that they reproduce the old result that I have, and then plus new terms. Right? So this does the job of reproducing the old stress tensor and then contains new terms. Now, what is the generalization of the stress tensor for the BC? We can play with three different combinations. Right, these are three different combinations that contains B and C, and then some supersymmetric derivative that are shared in different ways. 1, 1, 2, and none, none, and 2. So the question is, what is the right combination of these objects that reproduces for the BC system the old result? So you can calculate each one of these. This one will be B gamma plus Z minus B dC. So all this calculation requires just 2 minutes each and a bit of patience. It's just that there are a few of them. So these are the three combinations. And if you look at the bosonic bit, they all look similar to the stress tensor we derived like a few lectures before. Right. So that stress tensor, the old one, was minus 2b dc minus dbc. So what should I do? Well, dbc comes only from here, so I should take this minus 1, right? dbc comes only from here, so I should take minus 1. And the other two combinations that I have to take are 1/2 and minus 3/2. So if you take this combination, right, minus 1, like here, then you sum 1/2 of this, you subtract 3/2 of this, what you should get is, for the z part, minus 2 bdc minus dbc, right? So you should get for the BC system the old sector, right? And you see this is minus, this is giving this, and this is minus 3/2 minus 1/2 is minus 2. It's giving this one. And then for the beta gamma system, you will get minus 3/2 beta d gamma minus 1/2 d beta gamma. Now, you see that the beta gamma system with this choice takes a very similar form as the BC system, right? Beta d gamma is the same form as BDC. D beta gamma is the same form of DBC. These numbers are slightly different, but that's good because they match the conformal weights, right? B had conformal weights too, and if you remember, I gave you a general formula with lambda at a certain point, and here there was lambda, right? And then we say, okay, in the system, BC system, we put lambda equal 2, and so that's we have lambda 2. So beta has conformal weight 3/2, right? And so that's why we have this 3/2. And this factor here was 1 minus lambda. 1 minus lambda was minus 1 for lambda equal 2. And here 1 minus lambda is minus 1/2. So you see perfect symmetry between BC and beta gamma, taking into account the conformal weight that you read again by this superfield expansion. Very good. Any questions? Yeah.
Why should dx d squared x give me a supercurrent and a stress tensor?
Why we call this supercurrent and we call this stress tensor? Yeah, so this guy is the, well, if you do the same combination here, you will get the contribution to the supercurrent from the ghost, right? So this guy has conformal weight 2, right? And this guy has conformal weight 3/2, right? If you count, this is 1/2, this is 1, 1 plus 1/2 is 3/2. So this is related to something like the graviton, and this is related to the gravitino. Yeah, not just because of the conformal dimension, but if you look at the x component, it's the same as before, right? Right. So this contribute. So the nice way just to understand where the different bits are, you look at the contribution coming from the fields you had in the bosonic theory, and you immediately see what that object is, right? So here you see this object. Okay, that's the stress tensor, the bosonic theory. So then this has to be the stress tensor of the full theory. What I'm saying is that I'm not pretending to derive a superstring from first principle, but I just want to give you the easiest and safest way to write the expression. And like this 1/2 is important, you'll see now. It just comes out from the calculation. You don't have to remember, right? Just do the calculation. Very good. So in the final 5 minutes, I can give you the last ingredients, and then you have all the results just to do a calculation which shows the critical dimension of the superstring theory. Right, the last ingredient I have to give you, right? So you see what we want to do is to take T total in Z1, T total in Z2, and extract the highest possible singularity. Right. When you do the OP. What is T total? Well, T total is T matter plus T ghost. So you see, it's exactly as in the bosonic theory, but both the matter and the ghost stress tensor have been decorated with further contribution. So the calculation has the same flavor as the bosonic string theory result, But now, in this OP, you will get 4 contributions from the X sector, from the psi sector, from the BC sector, and from the beta gamma sector, right? So you just calculate those 4 contributions independently, and you want to sum the contribution to the quartic pole, which is a number, from each one of these calculations. Now, what do you need to have in order to get the OP, this number? You need to have the OP of the elementary field. So the final ingredient I want to give you is the OPE in terms of superfields. Right? So this is a whole superfield. This is a whole superfield, right? This is dimension 1/2. This is dimension 1/2, and you see the right-hand side as dimension 1. It's 1 over z. Now, this is a superfield, so it depends on both the small zeta and the Greek zeta. And this combination here is called the superdifference. Right? Because it's standard difference decorated with an extra z term. It has nice transformation property that I will not discuss. That's what fixes this sign. Very good. So what you can do? Well, you can do the same thing. You take this guy, you expand in field. You take this guy, expand in field. You expand here in term of zeta 1 and zeta 2, you match left-hand side and right-hand side, and you read the OPE of each component. Example, from here, you read psi m, psi n is proportional to eta mu nu, z1, z2. This is the easiest one, right? This derivative will kill zeta, the Greek zeta. This derivative will kill the Greek zeta. So the component, the term independently of the Greek zeta is psi psi. And then if you want to extract the term independent on the Greek zeta, you kill this. And you get that. And the sign goes away because of this I. So just do the calculation and you'll see. And then what I need to give you is the OPE between B and C. And this OPE between B and C is zeta 1 minus zeta 2 divided zeta 1 minus zeta 2 divided zeta 1 zeta 2, but this you can kill. Very good. So from here, again, you can expand in components, and let me give you one example. The OPE between the new fields, beta gamma, and the OPE between beta gamma is minus 1 zeta 1 minus zeta 2, and the OPE between gamma and beta is plus 1 zeta 1 minus zeta 2. Right? So what I want to stress here is that there is a sign difference between the BC system. So the BC system had very similar OPE, but with the same sign. This was related to the fact that the B and C were anti-commuting variable. Now this goes to beta gamma have the opposite parity, right? If B is anti-commuting, then B is commuting. And if C is anti-commuting, gamma is commuting. So beta gamma are strange objects. They have half integer weight, but they are commuting variables. And this is not strange because we expect that gamma is the partner of a local symmetry. The local symmetry we were discussing was local supersymmetry. The parameter of local supersymmetry is a spinor, right? It's an anti-commuting object. And so when we do the Fadel-Popov trick, we will change its nature, it will become a boson. Okay, you have all the ingredients, and it just requires a bit of being careful with signs when you swap anti-commuting thing with derivatives and putting everything together. But you can see that this C total, takes this form. D over 2, this comes from the X. This was the old result. Then you have plus D over 4 yes, and this comes from the psi's. So the matter contribution to the central charge is 2/4 plus 1/4 is 3/4 D. Right? D is the same as before, right? Because the X and the psi have an index M, they all contribute the same, right? So you do the calculation for one and then you multiply by D. And now you have the Gauss sector, right? And the previous calculation for the Gauss sector was minus 26, right? This is the BC system. This was, sorry, this is C total divided by 2, and so this is 26 divided by 2, right? So this was from the BC system, so if this guy is not there, it's fixing D equal 26. So the final contribution is from the beta gamma sector, so from this contribution here. Very similar calculation to the BC, you have to do the contraction, you use this OPE, just crunch, and what you get is plus 11 over 2. And now you want to set this equal to 0, right? And so you say minus 26 plus 11 is 15, right? So if D is equal 10, this 10, so this is 15 over 2. If D is equal 10, this is 5 over 2, 5 times 3 is 15. So this equals 0 implies D equal 10. So the message I want to give is that it's not a mystery, it's just that you have new sectors. These new sectors add contribution to the central charge. We can calculate this contribution to the central charge in the usual way by doing the OP of the stress tensor. We impose conceptually the same constraint, and we find a new result for the dimension. Okay, any questions? Okay, so tomorrow we will discuss the spectrum and the deep brains in this setup.